So welcome to the first lecture of the third week of this course in machine learning. This week we will focus on representations. So first a few words about representation. This is a course in machine learning, so you can wonder why should we spend a whole week on representation. So I want to show you this triangle of three abstract concepts that are really the key, the backbone of concepts for any kind of work in machine learning. So we have the concepts of representation, we have the concept of problem solving, and for problem solving, it's a little matter of taste, what term you like. I prefer problem solving. Some people would say reasoning, other people would say decision making, but it doesn't really matter. And of course, the representation part as such is more the core declarative part of the system. But the representation in that sense is only there because it should support problem solving. So this means that when we talk about a representation, it's absolutely necessary also to talk about that kind of problem solving that really fits that representation. So this you will see that during the week that we will have these so-called representation issues, but essentially when we talk about it, it will in the end be a mix of pure declarative aspects and more problem-solving aspects. Also, of course, because it's a machine learning course, it's an important issue. What would learning mean? What form would machine learning take in that specific form? This means that in several of the lectures this week, we will also touch the learning aspects of these representations. So I want to comment on something that I personally find very important. So the message here is that computer science is, of course, an engineering discipline. And artificial intelligence, therefore, is an engineering discipline as well. So actually the choices of representation and problem solving schemes are and should be based on many pragmatical engineering decisions. And of course, the same domain and problem can be modeled in any of the alternative representation and problem schemes, theoretically. Not necessarily it is as convenient to do it in all these forms, but it could be done. Also, when we work on a specific domain, we may use not only one of these schemes, we may use several of them. And we may map what we described in one scheme onto another scheme. Because there are many purposes here. One purpose is to understand what we are doing, is to have a kind of representations that is easy to understand for humans, for people involved in the whole process of working with the domain. The other aspect is that the representation should be a convenient base for an efficient implementation. So it may be so, for example, we will see that later, that we can have a neural network representation which is then mapped totally onto an array representation, and then the computation will happen in the array representation. So problem solving and machine learning for a domain may be more feasible to implement in some of these schemes, while some other forms may be useful for other purposes. So the bottom line here and the summary of this slide is that nothing is absolute here. Everything is relative. Representations and problem-solving schemes are tools in our toolbox, and we have to pragmatically choose the most suitable combination for a particular problem area. So, of course, one always have to make a choice. What is the most relevant subteam to focus on? And I've made a decision to spend most of these weeks this week on 5 kind of representations and problem-solving schemes. And the 5 I've chosen are decision trees, Bayesian networks, neural networks, genetic algorithms, and logic programming. So there will be one lecture on each of these themes. So for each of these lectures, I decided upon a structure that I will try to stick to. So for each of these representation schemes, I will talk about something general, about the general characteristics about them. I will talk also a little about the kind of sources of inspiration, how they come to be developed. I will try to describe the kind of core components, and in most of the cases also say something about structural aspects of the representation. Finally, I will look into what kind of problem solving is typical for this representation, and in the end comment on what could it mean to do machine learning for this kind of representation. So even if I did choose 5 sub-themes for separate lectures, there are other subtopics too that is worth mentioning. These subtopics has typically been very, very important for work in machine learning, and indirectly these subtopics is relevant and can come into play in machine learning. It wasn't really possible or relevant to make a lecture of each one of these. So what I will do is that I will now shortly comment on these sub-themes. I will start with say something about list structures and list processing. I will say something about arrays. I will say something about graph theory and graph search. I will talk a little about semantic networks, and finally I will say something about production rule systems. So starting with list structures and list processing, so which has been for a very long time the most established form of representation in artificial intelligence. The cornerstone here is to look at expressions in the form of lists, where a list can be either a number of atoms, but they can also be the elements can also be lists recursively. So typically what you end up is with a gigantic structure of nested lists. The role and interpretation of the atoms and lists in various positions in these structures are typically defined for each domain. This creates a great flexibility to design any kind of system you like, but the problem is, of course, that the language itself lacks some semantics that can be shared across domains. The problem-solving paradigm coupled to lists is functional programming, and that's the computational model used for computing list structures in artificial intelligence. Computation here is viewed as a recursive application of mathematical functions. So you can see it as that you have a recursive structure of functions working on a structure of lists. It's a declarative programming paradigm. Programming is done with expressions in what's typically called statement in programming. And there is a very long history for this. Functional programming is based on work in the 1930s, where something called lambda calculus was invented. So the most well-known language in this genre is Lisp, which is the second oldest program and still used. Lisp has been used extensively for all kinds of applications. And many times, even if you have started with another kind of representation, semantic network, production rule system, and so on, you have in the end mapped those representation onto pure list structures and Lisp-based functions. So in the end, you can see an example of that in that genre, where a very simple semantic network has been expressed in a Lisp format. So now let's look at one form of representation that is very basic for most programming paradigm, and still also very extensively used in many machine learning applications. And this form of representation is arrays. An array is a well-known phenomenon. It's an ordered n-dimensional collection of items, where these items or elements can be identified by one index or synonymously by a key. Many times the word table is used synonymously for array, and if you conceptually have what you think is a table, it's very straightforward to map that onto some kind of array. Then there are some other concepts. So the term vector is used to refer to a one-dimensional array. Also, tuple would be a better word, more mathematically correct, because a vector is an entity of its own in mathematics. The same way for the concept of matrix can be represented as a two-dimensional grid, and you could talk actually about two-dimensional arrays as matrices. Even if also matrix is a separate kind of mathematics, really related to linear mappings. So, and finally, there is a third concept that occurs in the machine learning literature. It is the word tensor. And also tensor is a special kind of mathematical entity, but you may decide to talk about the multidimensional arrays, 3, 4, 5 dimension arrays as tensors. And I would say that even for many of the representation we will talk about in the coming lectures, many times in the end, when real computation should take place, these representations are mapped onto some array structure with the purpose of doing basic computation in the form of array processing. So this second slide is just an illustration of the last, actually showing in some graphical form what is typically meant in the literature by a vector, matrix, and tensor, in the sense of being different variants of an array with various dimensions. So now let's turn to another very important topic, actually. In mathematics, graph theory is a study of graphs, which are mathematical structures used to model pairwise relation between objects. A graph in this context is made up of vertices or nodes, which are connected by edges or arcs. Actually, graphs is a very powerful tool for modeling and also being a basis for various kinds of implementation, both for problem solving and machine learning. So knowing something about the terminology of graphs and the properties of graphs is a background knowledge that makes a lot of sense and is virtually invaluable in work in this field. So apart from having a basic structure, there are some distinctions. So graphs can be undirected or directed. Directed means that the edges has a direction. It can also be so that there are some numerical measures coupled to the vertices. You can typically call them weights. There are also issues like connectivity, where there are paths between specific pairs or subsets of nodes. There's also issues of whether there are cycles in a directed graph or not. And there are more specific concepts like bipartite graph, and certain distinctions. So to know something about the issues of graphs and the terminologies related to graphs is very important because it's commonly referred to in all kinds of contexts that we will go into. So coupled to graph theory, you find on this slide a list of so-called classical graph theoretical problems, ranging from the old problems, the 7 bridges of Königsberg, that could be, of course, easily mapped onto a simple graph, the traveling salesman problem, various problems where you find path with certain properties, for example, a path that visits each vertex exactly once, or paths that uses every edge exactly one, onto problems where you assume to find subsets of the graph which spans all the edges. These problems maybe not you may not view them as directly relevant for either artificial intelligence or machine learning, but indirectly in many problem-solving situations, these variants of these issues will occur, so to say, in disguise, because many times when you model your problem, even if you express yourself in graph terminology or not, essentially you handle your problem as if it was a graph theoretical problem, and therefore for the classical issues in graph theory will occur. Closely related to graph theory is graph search. And actually graph search has from the start been a core methodology in artificial intelligence. And of course, machine learning as a sub-area inherit the dependence of these techniques. So many times problem solving will take the form of search. Learning will take the form of search. And therefore, the vast repertoire of search strategies that has been developed is of relevance. And on this slide, you find a kind of overview of the kind of strategies developed historically. I will not go into great detail because this is not the main topic of this course. But obviously, when we come into the algorithmic parts later in this course, reference to search techniques will be imminent. So essentially, as you can see, there are 3 categories of search strategies. One category called brute force, which is essentially that they are uninformed. The second group is here called informed, which means that they are guided by some domain knowledge or heuristic knowledge to proceed. And the third category is termed local search. And within each of these main categories, you have the specific types of algorithms. So my recommendation is that you may look into some of these detailed algorithms yourself, because there will be a lot of references coming on if you are not already have a good knowledge about these issues. So now we leave the more formal matters and look into 2 kinds of representations that has been used a lot for practical problem solving historically. And one of these is what's called semantic networks, or synonymously conceptual graphs. So semantic network is a graphical formalism that represents semantic relations between concepts. It's a directed or undirected graph consisting of vertices which represent concepts and edges which represent semantic relations between concepts. So the edges can be labeled in arbitrary ways, which we'll see in the coming slide, but there is a small set of standard edge types that occurs frequently in many of the cases developed. So ISO is a kind of relation which corresponds to what was described on an earlier lecture, corresponds to a generalization relation in a taxonomy. Has, it's a standard attribute feature relation. So, for example, an object has a property. Part of is what you call a component relation, which means that one kind of entity is actually physically part of some other entity. Finally, you have a certain kind of causal relations related to actions or events. A drawback with semantic network representation is there is no agreed upon notion of what given representation exactly means, or some formal semantics, as there is in logic. So here you can draw a parallel to the list representations in Lisp, for example, where there also is everything is decided from case to case. So if you go from one domain to another, you find syntactically it looks the same, but the intention of what is in the representation is domain specific. So therefore, it's much more difficult to compare what is done in different cases. There are also ways of expressing the basic semantic networks. So it means that an edge not only relates to a concept, but an edge can be a network of itself, which means that you can express things like a person believes something, and something is not just a simple fact. It's a more complex situation, and that complex situation can in turn be represented by a network. So on this slide you see a few examples of semantic networks. You can just have a look and the intention is of course to give you a flavor how things are expressed in this kind of formalism. A few general messages could be that as you see, as was told on the earlier slide, on one hand there are a few standard attributes that occurs in many cases, like generalization, relations, attribute realizations, part of relations, and so on. While there is also a bunch of relations or edge labels that are totally domain specific and tailored to the current situation. It should also be obvious to you that if one wants to work systematically and professionally with this kind of representation, it's very clear that the graph theoretical issues come into play. So finally, let's turn to something termed rule-based systems. So actually rule-based systems is a kind of systems used a long time in artificial intelligence to implement what was also earlier called expert systems. And there are various synonyms. You can call rule-based system if-then rule systems, or if-then systems, production systems, and so on. The idea with rule-based system is to try to separate out declarative knowledge from procedural knowledge. And the rules specify each possible inference step in a declarative way. And normally there is a very simple syntax. So there is a rule syntax saying there is an if part with a number of conditions, and then there is an then part with something with a list of actions to perform if all the list of conclusion, the whole list of conclusions is satisfied. The problem with production system, as for semantic networks and also list representations and so on, is there is no well-defined semantics for what actually is intended. Because it's kind of obvious that the syntax for a rule is very simple. So actually, it's up to you when you design your rule-based system to define what you mean by rule, the intention of a rule. So a rule could be that the if part looks at the situation and have conditions that evaluates that situation. The then part is a set of actions acting on that situation. But it could also be that the if-then construct models something more close to logic, where the if part is a premise part and the then part is a conclusion part, and so on. Almost all rule-based systems share some core parts. So there is always a collection of facts, and the collection of facts, you can say, represents the problem state. And then there is a collection of rules called a knowledge base, which can act upon the facts. So there is a cycle. So there is the computation is a cycle, where in each step of the cycle, the collection of rules potentially work on the facts. Some rules becomes relevant because the condition part is satisfied. So then these rules fire. And there is an inference engine that handles this matching process of which rules that apply in a certain step and carrying out the relevant actions. And there are many different kinds of systems, and actually you can use rules both in a forward manner and backward chaining manner. I mean, forward means that you go start with evidence and try to infer consequences, while in backward chaining you look at consequences and try to infer what reasons or evidence is most likely to have led to these consequences. And of course, there always have to be some criteria for when we have reached a satisfactory solution. So on this slide, you find a graphical depiction of what can go on in a rule-based system. Actually, this kind of picture is not only relevant for production system, but for most of the systems we look at, because what is included in this picture is both, as you see at the top, the relation to an external situation where the system interacts with that environment, but it's also a relation at the bottom where you can get a graphical model how the development of the system can take place. So of course, none of the systems we consider here will be useful if there is not a user interface where the behavior of the systems can be made explainable. And of course, we also need a kind of developer interface where users or humans involved can add new knowledge. Not everything can be learned. You also have to, even if you have a powerful learning mechanism, you have to incrementally add new knowledge to these systems in order to be useful. So the intention of this slide is only to give you a flavor for how a rule-based system can look like. Actually, this is an example of a rule-based system that is basis for a diagnosis system. So please have a look, and hopefully you get a good picture of how things are typically done in this kind of representation. This was the end of this lecture. Thank you very much for your attention. The next lecture will be on the topic of decision trees. Thank you. Goodbye.